So let's revisit problem 1. We had this nonlinear consumption term that we added to our differential equation, and this is the Michaelis-Menten expression for enzymatic reactions. The shape is like this. So it starts out the consumption rate versus concentration starts out at 0. As you increase concentration, it goes up, and eventually it saturates at a value of Vm. The value Km, the parameter Km, gives us the concentration at which Vm is 1/2. If we take ourselves only operating in this limit here, in a limit where C is less than Km, we can approximate this as approximately linear. So we can say that Vmc over Km plus C is approximately Km over 2, right, Vm over 2 Kmc. And this approximation is probably realistic if you consider that we're going to be working in a very low concentration limit, right? This is the case where oxygen is diffusing into these cells, and it's going to be scarce, right? We're not operating up in the saturation or the approach to saturation. Yet at the same time, we can take the calculation and work with it, and we'll know at what point does this approximation fall apart, because we'll know when we start getting up to the higher concentrations. So we'll have a pretty good idea of where it's valid. So if we start with that, and this was equation 5 from problem 1, and substituting in this for equation 5, we now can write our differential equation, our partial differential equation, this way. So that's the replacement for the original. Substituting in the radial coordinates and taking the spherical approximation, we have this. Again, this is the new and improved consumption term. Here are our boundary conditions, and here is our initial condition. So here we have a partial differential equation. It's a second order in R, which means we have 2 boundary conditions and 1 derivative with respect to time, so we have 1 initial condition. And this is the problem we want to solve. Again, we want to move to dimensionless values, and we'll use the same dimensionless parameters we had before, right? So this is the same as problem 1. We have rho, tau, and chi for dimensionless position, time, and concentration, and then nu and kappa for the Michaelis-Menten parameters. We take the substitutions again, so the derivative with respect of concentration with respect to time. This is the first term in the Laplacian. This is the second term in the Laplacian. This is our Michaelis-Menten consumption term, which turns into here. So this is the new part of our solution. Substituting these in, we wind up with this partial differential equation, which looks very similar. Only difference, again, is this last term. And again, the same boundary conditions and initial condition we had before. So this is the partial differential equation, 2 boundary conditions, and 1 initial condition. This is a nonlinear expression, so we can linearize it by making a substitution that u is equal to rho chi, and following through, just as we did in problem 1, these are the same expressions up until here. Now we have a new expression for the last term in the partial differential equation. Substituting in, we get a bunch of cancellation, we get a bunch more cancellation, and when we do that, we wind up with this differential equation. Again, it's the same as we had before here, except that now we have a different form for the last term on the right-hand side. The boundary condition, this one holds the same. This one holds the same. And we still have the same initial condition. Now, this set, zoom out. This set of a partial differential equation, boundary conditions, and initial conditions, I think this is probably solvable by separation of variables. I think. And that might be something for us to go back and do at a later time. But right now, we just want to get the steady state solution. And making then the substitution, that derivative of concentration with respect to time is equal to 0. That gives us du by d tau is 0, which gives us this ordinary differential equation and two boundary conditions, which is solvable. Hooray! Now, I solved it, but I'm not writing out the details, and in fact, Mathematica does a much nicer job at really consolidating this. And the solution is that u as a function of rho is equal to the hyperbolic cosecant of the square root of nu divided by 2 kappa times the hyperbolic sine of the square root of nu divided by 2 kappa times rho. And this is the solution for our problem in the case that the concentration is less than K sub m.